Hello and welcome to this homework help video. Here we're going to discuss a problem where we're going to be looking at light from an atomic source, and we're going to be using some common formulas for light, including the energy and frequency of light, and then something new that you haven't seen in the previous video for problem number 1 is we're going to look at something called the Doppler effect, and that's going to be part C. Okay, so that's the part that is new that you would not have seen in problem 1. Well, what are our calculations? Let's do each part. Okay, so in the first part, in part A, we're asked to find the frequency of light given its wavelength. So we know we have a certain wavelength. The wavelength that we are given here is longer than visible light because it's thousands of nanometers. That means it's infrared light. Okay, so longer wavelength, lower energy than visible light. Let's make ours a little bit longer than the number here, so I'll use different numbers. I'm going to go ahead and go with 2000 nanometers, so deeper infrared. Okay, infrared spreads across a larger range than visible light. All right, and now let's make our calculation with the formula. This is probably the most common formula of all the formulas for light that says the speed of light is equal to the wavelength times its frequency. And since the speed of light is a constant, we can always use wavelength to find frequency or vice versa. So I'm going to go ahead and find the frequency for my different value of wavelength than you're using, and that's just going to be c over lambda. The speed of light in meters per second, we'll go ahead and use meters for clarity, is going to be 300 million, or 3.0 times 10 to the 8 meters per second. And then our wavelength in meters would be 2000 times 10 to the negative 9. So 2000 times 10 to the negative 9. Not proper scientific notation. I'd want to move the decimal place over from where it is and end up with actually 10 to the negative 6, because 2000 nanometers is the same as 2 micrometers, or 2 microns. But we'll leave it this way. And let's go ahead and make that calculation. So over here for f, so we want to label this variable, okay, because we're going to use it again. So we're going to call this f for frequency. And we'll just set up our formula here. So in the numerator is our speed of light. Okay, and then in our denominator, of course, we have our wavelength. Okay, I will go ahead and clean it up, put in proper scientific notation here in the calculator so you can see what I mean. So it was times 10, and then it was negative 6 over here. All right. Okay, so let's close that. So we can then see our frequency. Our frequency is hundreds of trillions of hertz, which is typical of light, even longer wavelength light than visible light. The frequencies are huge. So 1.5 times 10 to the 14 hertz. Okay, so that's the first answer to part A. So moving on to B, we're asked to find the energy per photon for this light. Well, that brings us to the second most important and common formula when you're working with light, and that is that the energy of an individual packet of light, the smallest piece that you can break light down into, called a photon, it's a particle of light, is equal to a constant of the universe called Planck's constant times the frequency of whatever type of light you are talking about. In this case, our 2000 nanometer infrared light. So we'll plug in the value. The Planck's constant is always the same number. It is a value of angular momentum, which isn't obvious here in the problem or anything, but that's the background. Okay, so it's a very small number. You can see it has an incredibly small exponent because it's about breaking the universe up into the smallest pieces that we can. So it's quantum mechanics, and it should be small. So 6.626 times 10 to the negative 34 joule seconds, and then we'll just multiply that by the frequency that we solved for, 1.5 times 10 to the 14 hertz. That's going to give us a value that we can go ahead and take a look at over here in Desmos with using our previous saved value of F. And so we'll just call this E for energy. I don't think we're going to use it again, but it's a good habit to get into. 6.626 times 10, and then we're going to have our negative 34. Okay, and then of course we just need to multiply it by F. Okay, so there we have our value. Okay, oh yeah, so I can't redefine E because E is reserved for exponentials. It's a particular number like pi, so we'll call this I. Okay, so there is our energy per photon. 9.939, we'll round that to 9.94 times 10 to the negative 20 joules. Okay, that's your baseline of energy. We convert that to other forms of energy, but we'll leave it there. All right, that is by far the most common metric form of energy, joules. Finally, something new, looking at the Doppler effect. So the Doppler effect is the idea that if a source of light has a certain wavelength at rest, which we would think of as measured in a laboratory or measured on Earth, if we have a source like a star that's moving very fast away from us, or a galaxy that's moving very fast away from us, or just very fast relative to us, the observer on Earth, we'll notice that that same known wavelength from some atomic spectra or similarly well-documented source has shifted. And so then there is a new value, a shifted value, which we can see here, shifting to either longer wavelength in the case of redshift, or to shorter wavelength in the case of blue shift. Red light being the longest visible light, blue light being the shortest of visible light, okay? So in the original problem, we can definitely see that it is a redshift because we went from 1130 to 130, okay? Both in nanometers. That corresponds to a certain direction. I'll let you look that up on your own. But as far as the formula that you need for this one, you just need the ratio of the velocities. So this is the velocity that you're going to be solving for. Okay, that's the thing you're interested in because you're using this shifted light to solve for velocity. It's light giving astronomers information about relative velocity. And that ratio of the velocity over the speed of light is equal to the change in the values of the wavelength over the wavelength measured at rest. So if we expand that delta lambda, representing the difference of wavelengths, then our formula will become V over C, so the ratio of the velocities, over the new wavelength minus the original wavelength. Okay. Now this would be, in this case, we will get a positive value because lambda prime is larger than lambda. The new shifted, measured, observed wavelength is longer than it is when that same wavelength is observed at rest. Then that means that when we solve for V, we'll get a positive value. That means that the object is moving away from us. A negative value, that means it's towards us. So the directionality is that positive is away, negative is towards. Okay, so there's like a positive number line leading away from you, and if you're moving along that number line in the positive direction, then an object is moving away from you. So let's plug in the numbers for this particular version. So V, and we're just going to have C, and then times this difference in wavelength over the original wavelength, okay? So I haven't chosen one with my new made-up numbers, but first we'll plug in the speed of light, so 3 times 10 to the 8 meters per second. Then we'll put in a new wavelength. If I've started at 2000, I also want mine to be redshifted like in the original problem. Let's have ours go up to 2280. All right, so yeah, it's kind of, maybe that's too similar. How about 2180? So we have 2180 and then minus 2000 all over 2000. And you might be like, wait, I forgot my exponents. But since it is a ratio and there would be a 10 to the negative 6, or, or in this case, negative 9, if I'm leaving all as 2000. So a 10 to the negative 9 up top, a 10 to the negative 9 down below, and they cancel. So you only care about, this just the easier part to write, basically the front of the scientific notation. It's the same ratio. All right. And so if we go ahead and plug in those numbers over here, I won't give it a variable name because we're not going to be using it again since we are nearly done. 3 times 10 to the 8 for our speed of light. Oops. All right, so to the 8 power, there we go. And then we're just going to multiply that by our difference of wavelengths. So our 2180 minus our original 2000 nanometers as measured in the lab. And then let's get that all over 2000. And it doesn't matter if the fraction goes all the way. The point is that we have a 2000 down below. All right, so there is our velocity. All right, and we have 6, 7, so 2.7 times 10 to the 7 meters per second. Now, obviously, that is a huge velocity, but those are realistic for very distant galaxies. Their relative velocity to our, observing here within our own galaxy, and it's not so fast that we have to worry about relativity. because we can see that it is less than 10% the speed of light, but it's still pretty darn fast. We only really have to use a different, slightly more complicated formula for things that are moving closer to the speed of light. So numbers that you would get, really close to that 3 times 10 to the 8, rather than this being over 10 times smaller. But anyway, that's an example of our calculations for a problem that involves common formulas for light and the Doppler effect to measure velocity by observing light. Okay, well, I hope this video has been helpful. Thank you so much for watching.